All right, so we're into week 8. We're still talking about acids and bases. What we're going to do today is we're going to take our ideas of Ka and the equilibrium constant, and we're going to say what happens when we start to mix acids and bases, right? So this week is going to be all about when you have an acid and a base present in our mixture, what is going to happen to all those equilibrium constants, what's going to happen to our equilibrium. Is it going to move towards products? Is it going to move towards reactants? Which sounds a lot like Le Chatelier's principle and the reaction quotient Q. We're going to use that stuff too. So let's jump into it. First, we're going to start by talking about bases and just kind of define what, if, instead of thinking about this in terms of weak acids, what if we think about it in terms of bases? And what you'll see is that, of course, it's pretty much the same thing. So let's do that. So first of all, with weak bases, we can define an equilibrium constant for weak bases as well. We're going to call it Kb because we're not terribly imaginative. And of course, Kb is going to be very similar to Ka, only instead of doing the concentration of H+, we're going to use the concentration of OH-. So Kb will always be the concentration of OH- times the concentration of the conjugate acid all over whatever the concentration of your base is. And this all, of course, comes from the standard reaction of base plus H2O, and then the product side of that is going to be the conjugate acid plus OH-, right? And so you figure out the equilibrium constant of that reaction, and we get the Kb expression that we have right here. Now, there's nothing difficult about this. This is exactly the same as everything that we've already talked about, so there's no surprises here with Kb. What I do want to say is what is interesting is what happens if you have the, what if you consider the Ka of your conjugate acid, right? Because the conjugate acid is also going to have, will have a Ka, and the conjugate base will, of course, have a Kb, right? So we can define the Kb as OH- times conjugate acid over the base. We can define the Ka of the conjugate acid is if we react the conjugate acid with water, right? If we put water on this side, we're going to have H+ and this conjugate base over on this side. And so basically what we get is what happens when you have these two things in the same solution is what happens when we take Ka times Kb, right? Ka will be, of course, the concentration of H+ times the conjugate base divided by the acid, and Kb will be the concentration of OH- times the acid over the base. And I'm taking out I should have taken out the conjugate in the first one, but because these are conjugates of each other, but this also works, right? I'm just going to say acid and base because the conjugate acid in the Kb expression is the acid in the Ka expression. And so, of course, if we look at this, we can start crossing stuff off because we have a base in the numerator, a base in the denominator, an acid in the denominator, and the acid in the numerator. So what we get is Ka times Kb is the concentration of H+ times the concentration of OH-. And what is that value, right? This is one of those values that that I'm hoping that you recognize. Right? This is one that we talked about quite a bit, is what is concentration of H+ times concentration of OH-. This is, of course, Kw, which is 1 times 10 to the negative 14th. So Ka times Kb equals Kw, right? When your acid and base are a conjugate pair, are conjugates of each other. And so really, this is the important thing of all this is that if we know the Ka value of an acid, we also know the Kb value of its conjugate base, right? If we know the Ka value of the acid, then we know 2 of the 3 variables in this, or 2 of the 3 terms in this equation. If we know Ka, we already know Kw, it's always 1 times 10 to the negative 14th, and so it's very easy to figure out Kb of the conjugate base, right? So this, of course, also reinforces the idea that if you have a large Ka, right? Kw is going to stay constant, and so that means that Kb has to be smaller. And so if we have a strong acid, then the conjugate base is weak, right? And so if we have a very strong acid, right, then the conjugate base becomes weaker. If we have a weak acid, the conjugate base becomes stronger, right? And so there's always this balance. Whoops, I lost my button here. There we go. So if we have their acids and base strengths are always going to be balanced, right? Strong acid is going to have a weak conjugate base. Weak acid is going to have a very strong conjugate base. And so being able to see that and recognize that is going to be really important when we get to reactions where we have both the acid and the base present in the same solution, especially if we start adding a conjugate base to our solution. And that's going to be kind of the next thing that we talk about. The last thing I want to do in this video is just introduce the idea of pKa and pKb. There's nothing, again, this is another one where there's nothing really new here, but you'll recall that when we did pH, right, pH equals negative log of H plus, right? We could also define POH, that is the negative log of OH minus, right? So the P in front means negative log of whatever, right? So negative log of H plus, negative log of OH minus. We remember that because the concentration of H plus times the concentration of OH minus equals 1 times 10 to the negative 14th, that means that if we add pH to POH, we're going to get the negative log of 1 times 10 to the negative 14th, and so that will equal 14. So the pH scale and the POH scale are inverses of each other, where when one is very low, the other is going to be higher, and they will always sum to 14. Right? You can take the negative log of both sides of this equation, and you will get, I guess, let's write that in. Negative log of all this times, I didn't leave myself space, but times the negative log of 1 times 10 to the negative 14th, right, is what gets us to this final thing here. So if we draw out all three steps of this process, right, we have H plus times OH minus gives us Kw. The negative log of all this stuff gives us pH plus POH equals 14. Knowing that, let's talk about pKa and pKb. Now, of course, pKa is just the negative log of the Ka, because that's how we define pK whatever, right? And of course, it's the same thing for pKb. Negative log of Ka, negative log of Kb. What we know about Ka and Kb is that Ka times Kb equals Kw. And so once again, if we take the negative log of each side, Ka times Kb, and we take the negative log of Kw, right, we know that Kw is 1 times 10 to the negative 14th, and so we know that the negative log of that will be 14. On this side, if we take the negative log of Ka, that's the pKa, and we can add in the negative log of Kb, and that gives us the pKb, right? So pKa plus pKb equals 14, right? So when we talk about pKa, right, we're going to use pKa in one of our kind of fundamental equations coming up here real soon. So I want to introduce this idea here. The pKa is just a way to get away from scientific notation, right? So for example, acetic acid, right, has a Ka of 1.8 times 10 to the negative fifth. We've already established this, right? That's kind of cumbersome to write. So instead we usually refer to acetic acid as having a pKa of 4.75, right? Which is just the negative log of this number, 1.8 times 10 to the negative fifth. This just gives us, it's a simple scale, it's the same scale, right? It just gives us a simpler number to write. The thing to remember about pKa is that the relationship is inverse, just like with pH, right? With pH, lower pH equals more acidic, right? With pKa, because we're taking the negative log, the lower the pKa, that equals a stronger acid, Right? So the lower the pKa gets, the stronger our acid is. The same thing is true for pKb. The lower the pKb, the stronger the base is. So we've introduced two ideas here. We've introduced the idea of Kb and just kind of what a conjugate, how we deal with conjugate bases, and we've also introduced the idea of pKa, which is just the negative log of Ka. So a couple of introductory things. In the next one, we're going to get to the actual like what happens when we start mixing these things together. So stick around for that one.